Hey there, ladies and gentlemen. This is Mr. Collins again. We're recording full style now on the iPad, so we're going full on because this is a pretty big subject. So if you're in first, second hour, I don't know where fifth and sixth hour are going to be, but we were talking consolidation. This consolidation in particular, we're talking about recursive functions versus explicit function. I thought maybe we should take some time and really work this crazy thing out. So before we begin, what we really have to establish is remind ourselves what is a recursive function, what is an explicit function. So having said that, when you're talking recursive, hold on, let me get this. This is freaking me out. Okay, when you're talking recursive, we're talking explicit. What you're really talking is whether or not you need the previous terms to define the next terms, or you can directly jump to the term you actually want. Man, this thing is slow today. Okay, here we go. So you're talking recursive, you need the previous terms. And when you're talking explicit, you're talking like a y equals equation, a direct line to the actual answer, where you can take an input and it kicks out an output. So take this first one for example. We have this input-output table. We need to define it recursively or explicitly. Either way, we have to figure out what's going on in our y values. So 3 to 7, that's definitely going to be an addition of 4. So let's see if that works out for the rest. And lo and behold, it certainly does. Now this tells us two things. One, it tells us we have a common difference of 4, but most importantly, it tells us that we're dealing with a linear function. So I'm going to write the explicit function first. If we know we have a linear, we know it's following y equals mx plus b. We just have to fill in the pieces, m being the slope, and b, of course, being the y-intercept. So looking at our table, we can pull those values very quickly. The slope in this case is going to be 4, and the b value is going to be 3. Now, recursive functions are a little bit different because we need the previous terms to do it. So we need a place to begin, so we'll go ahead and write in a start value, or start at value. In this case, it's going to be 4, simply because it's the first one listed in our table. So to get our next term, we'll take our previous term and then add 4. And that'll give us our entire function. So the recursive function, the way it's to be written out, is very much in words. You see kind of example down here in words. So just know that the recursive function and this explicit function mean the same thing. It's just different ways to get it. So let's check out the next one. The first term is 80. To get the next term, divide the previous term by 2 or multiply it by a half. So we can actually fill in our table. Starting at 80, multiply by half or divide by 2 gives me 40, 20, 10, and then 5. Now the explicit rule, we first have to determine what kind of function this is, meaning that we really have to look at these jumps. So check this out. That's going to be a times 1/2. That's going to be a times 1/2. Now we don't have a difference this time because it's not going to be common. The jumps are too varied. What we do have is a common ratio or common multiplier, meaning this guy is going to be exponential, a times b to the x power. Now again, we need to kind of figure out what the pieces are. That's going to be our y-intercept. And this guy right here is going to be our common ratio. But we have those already kind of predefined. So we're looking at starting value at 80 as a y-intercept times 1/2 to the x power. Now this fits what we already know. We know it's decay, so it's going to be going down. It is. We know that we started at 80, common factor half. So let's check out the rest of them. So I don't have them labeled anymore, but this is recursive, explicit, and then that. Now we don't have either of the functions, which means we definitely need to start over here at the table. And let's figure out what's going on. Well, from 70 to 79.5, I'm losing 0.5 values. Here I'm losing 0.5 values. Looks like a pattern to me, boys and girls. That's 0.5. Boom. That's 0.5. Wow. Okay, so we might lose 0.5. So in terms of the recursive rule, we're going to start at, in this case, 80. And then the next term, is the current term, where we are right now, the current term, minus 0.5. In other words, kind of what we discovered over here. This is the explicit rule. Now, if we're losing, we have a common difference. We're definitely going to be dealing with y equals, y equals mx plus b. Again, the m being the slope, b being the y-intercept. Either way, the slope in this case is negative 0.5, and then we're going to start at 80. Yeah. Okay, so first term is 10, then double each term to get to the next term. So first term is 10, double to get to 20, double to get to 40, double to get to 80, double to get to 160. 10, double, 20, double, 40, double, 80, double, 160. Man, if I'd done it right the first time, I would have ran into this mess. Now, we don't have a common difference, and the reason is because that's plus 10, that's plus 20, but we do have as a common multiplier of a times 2. So this tells us something really important, that we're dealing with an exponential function, y equals ab to the x power, where a is our y-intercept, and b is going to be our common ratio or common multiplier. So when writing this function, let's find those pieces. A, y-intercept, there it is. So we have 10. B, common multiplier, there she is, 2 to the x power, and that is a times. So we've got a couple more here. This continuation is actually no different from what we have been doing. So we're given the table. Let's evaluate the table first. Let's find common difference if we even have one. That's not going to work. That's going to be plus 4. That's plus 20. Let's see if we have a common multiplier. I'm looking at it times 5. Oh, look at this. Times 5. Oh, I think we're going to get it times 5. And yes, if you want to check with the calculator, that is times 5 as well. So again, importance. This tells us we're dealing with exponential. So we have a times b to the x power. Looking for the pieces that we need. A is going to be 1. B, the common multiplier, shall be 5. And that be it. So that's your a value. And then these guys are your b value. So how do we actually generate that using the previous terms? Well, we got to have a starting point. So we're going to start at 1. The next thing that we're going to get in line is going to be the same thing as what we have right now, times 5. Which is a kind of interesting way to write it. It's an old school way to write it, but that's how I like to do it. Start at 1. The next term is the same as what you have right now, times 5. So moving to our last one, looks like we need to calculate for this guy, 1.1 to the x power. So the question is, well, what do we do first? To me, it's easier to go to the table, simply because I have a pretty easy way to do that. I have the explicit rule, so what I really have is the ability to make a table. So 1.1 to the x power, and for y equals, there we go. So let's just filter this in. So I'm just going to abbreviate. So 1.5, 1.6. 1.8, 1.9. Oh, you know what? I messed up, didn't I? Let me back that up. There she is. Okay. And if you're wondering how I knew I was wrong right away, I didn't look actually, but I realized that this tells me that this function is really 1 times 1.1. So our starting value is 1. That's just 1.1. That's better. 1.3, 1.5. Okay. So now we have to deal with our explicit rule. I'm sorry, our recursive rule. So we need a starting value. So let's go ahead and start at 1 again, because that's what we have here and for our formula. 1 times 1.1. So another way to write this explicit equation is 1 times 1.1 to the x power, because of course we can multiply anything by 1. So starting at 1, so what we get next is going to be the same as what we have right now, times 1.1. Now, if you're wondering where I'm getting the 1.1 from, well, it tells us right here. That's what we're multiplying by. That's our common multiplication factor. So that's, of course, what I multiply 1.2 if I'm there right now to get to 1.3, or 1.3 if I'm there right now to get to 1.5. Okay. Last set. Now, this is one I can't necessarily do for you, but I can give you some advice on how to actually create this. You have to create your own. I kind of suggest starting with an explicit function. So step 1 would be this guy right here. You don't have to, this is just advice. But step 1, I would make my function, and I have to really choose like linear or exponential. So once I've come up with that, let's say I choose linear and I want to use y equals something x plus something. So this, of course, being your slope, and this, of course, being your y-intercept. I just now filter that in. Well, of course, your y-intercept is going to be this guy right here, and your slope is going to be that common addition problem. So I'll give you a sense how to create your input-output table. Once you have that, well, it'd be really easy to kind of write your recursive function, because the start value would be the same as the y-intercept. See how I'm color coding it? So the start value would be your y-intercept, and then the actual wordage of the recursive function. If you want the number that comes next, you got to take the number that you have right now, and then in this particular case, add the slope. So you can see very clearly these pieces show up in more than one place. So the start value of your recursive function is a y-intercept in your the start value in your recursive function is the y-intercept of your explicit function, which is also the zero value in your input-output table. The addition or subtraction or multiplication or division problem in your recursive is your slope or your common difference or common ratio in your explicit, which is the jumping in your table. Now that's why this is really, really important, because you want to make sure that you're having all these pieces kind of line up. And you can see that in almost every example that we've shown. Look, here is the start value, y-intercept, y-intercept. Here is the common difference, common multiplier, or not common ratio, and that would have been the actual multiplication jump here as well. And again, you can see it in every single example. So here's the common ratio, here's my common multiplication factor, multiplication jump throughout, y-intercept value, y-intercept value, y-intercept value, y-intercept value. So the reason we have these three side by side is to hopefully get you to realize that these are equally good representations of whatever you happen to be doing. So just something to consider for the future. So if this helped, I'm happy it helped. The video will be available. We'll post that at Bodo. Excuse me. So you can definitely use it for your upcoming tests. You guys have a great day, and I'll see you tomorrow.